Hello everyone to this video on Nonstochastic Contextual Combinatorial Bandits, which is a work that's going to be appearing at AISTATS 2023. This is a joint work between me, Lukas Zierahn, Dirk van der Hoeven, Nicolò, Cesa-Bianchi, and Gergely. We're going to start by looking at by an introduction, and we're going to look at a real-world scenario where this kind of algorithm that we're going to be looking at is going to be applicable. So we are going to consider a recommendation system. First, you have some information about a user, which you're feeding into your recommendation system, and your recommendation system is then going to recommend a collection of items. So if you're Spotify, you might want to create a playlist for a user. If you're Netflix, you might want to recommend not one movie, but multiple movies at a time. And then if you have ads on your website, then there might be more than one ad at a given time, and then you have a collection of ads you're trying to recommend. You then incorporated some user feedback into your recommendation system, and this is basically the setup you have. We can formalize this idea in this following slide. So our input is going to be an action set, calligraphic A. And A is going to be in 0, 1 to the k. So these are going to be vectors of length k, and the entries are going to be 0, 1. And this is depending on the problem you're considering. Then we have a context space, calligraphic X, and the vectors here are size D, and we have some distribution capital D over X. And then in each round, T and T, our non-oblivious adversary picks a loss matrix theta t. The environment draws an independent context vectors. So the vectors are not adversarial. The context vectors are not adversarial. These are stochastic, and these are independent. And we are also going to assume knowledge of the distribution D later for our analysis. The learner observes xt, and then given xt, we can pick some at from our action set. And finally, we incur the loss xt transposed theta t at. And this loss is linear in both the context and the action. There are two different settings here that are important. The first one is the semi-bandit setting, in which we gain this feedback where this dot is element-wise multiplication. In that case, we can see all the losses we incur decomposed into the action vector. And in the full bandit setting, you're just going to see the loss we actually incur. Now, with this basic setup out of the way, we only have to define regret. And regret is going to be the best, we're going to compare ourselves to the best stationary context to action mapping. That's going to be pi of xt. That's going to be our comparator, and otherwise this is the normal loss formulation. All right, we're going to now come to our first algorithm called CO2 FTRL. This is going to be for the semi-bandit case. So this is going to be the algorithm, and FTRL stands for follow the regularized leader, which is a well-known class of algorithm that's being applied all over online learning. And this algorithm is an instant of this learning algorithm. Specifically, we're going to observe xt first, then we're going to compute a bar t, and a bar t is going to be the point in the convex space of our action set that we would love to play if we could, given by a follow the regularized leader. Theta tilde s here is some, in this case, biased estimator of the actual theta. And the bias is going to be controllable in our analysis. You can also use theta hat, which we're going to look at in the next slide, which is going to be an unbiased estimator. But here we are using theta tilde. And now we have our point we would love to play a bar t that we cannot play, and we have to find a distribution over the action set such that in expectation we are playing a bar t. This in general can be computationally hard, but there are many cases for which this an efficient solution exists, for example AISTATS. Then we mix in some exploratory set, some exploration, and we draw our action we played. And then we can compute theta tilde t just based on the observation we have in this semi-bandit case. And we can actually take a look at how theta hat t looks, what theta hat t looks like, and this is going to be the unbiased estimator that corresponds to theta tilde t, which is going to be similar but biased. And here the important part is capital sigma tk is the expectation over x and at's distributed of pi t, and this is where the t comes in, given x. So there's a dependency between the actions and the contexts here, because we choose the action with regard of the context. If your contexts are not a parameter of the problem, then xt transpose, if this is deterministic, then you can just consider sigma to the -1 to be an importance-weighted estimator. And you can recover a normal combinatorial bandit case. theta hat t we can then show to be unbiased. We define theta hat t also here in terms of columns. So we write dot k to determine to mean the kth column of the matrix theta hat t, right? And then if we take the expectation of theta hat t in the kth column, then we can just plug in the definition given above. Then we know matrix multiplication is linear, so we can pull the expectation inside. And we already recognize that the expectation of ATXT is going to be the same thing as capital sigma t. And this is also the case because our context distribution is stationary and does not change. And then we used pi t in the definition of capital sigma tk. And then these cancel, and we are just left with theta t in the kth row. Right. And then the regret for CO2 FDRL is going to be of this form, where k is going to be the length of the vectors in our action set. M is going to be an upper bound on 1s in the vectors in the action set. Sigma, capital sigma, is going to be the covariance matrix of the context, and lambda mean of capital sigma is going to be the smallest eigenvalue of that covariance matrix. Small sigma is going to be a bound on the context vectors, and T, capital T, are the number of rounds we are playing. Next, we're going to come to EXP3 tensor. EXP3 tensor is the algorithm we're presenting for the full Bandit case. And here we start off by finding a probability distribution mu over the action set, which follows by the Kiefer-Wolfowitz theorem. Similar to the semi-Bandit case, this is not always efficient. However, this is efficient for many action sets like aim sets, for example. Then we observe xt, and here we are following an EXP3 style update. We are also using theta s tilde here. This is a different theta tilde than compared to the previous algorithm. However, it follows the same function. This is a bias estimator, and we're going to have a look at the unbiased estimator in the following slides. And then finally we draw our AT given the distribution where we use the normal EXP3 kind of update plus some exploration which we found earlier. And then we just update theta tilde t. So we find a new theta tilde t with the current time step t. Before we can introduce the unbiased estimator, we first need to introduce tensors. In our case, tensors are always going to be four-dimensional of size d, d, k, k, where d is the size of the context vector and k is the size of the action vectors in our problem. Tensors can really be thought of as multidimensional arrays. And matrices, of course, can also be thought of as multidimensional arrays in 2 dimensions. Still, we define interactions between matrices and between matrices and vectors. And we can define similar interactions for our tensors. So let's say phi is a tensor, and we have a matrix theta. Then we're going to consider phi acting on theta. This is going to be a matrix again, and it's going to be a matrix of size dk. And the ikth entry of this matrix is going to be given by the formula on the right-hand side. And in a sense, you can consider the second dimension of phi, the one indexed by a, is acting on the first dimension of theta, and the third dimension of phi is acting on the second dimension of theta. And then on the right-hand side, we're just going to have a real number remaining, where theta ab is a real number multiplied by phi I a b k, which is also a real number, and it all adds up. We're also going to introduce a lemma. Let D, C, and B be matrices of appropriate sizes. Then D times C times B transposed is going to be the outer product between D and B acting on C. So this is going to give us a tensor. And if we then use this definition of a tensor acting on a matrix, we're going to recover exactly DCB transposed. All right, we are now going to store this up here because we're going to need it in a second. And we are going to come to the unbiased estimator of EXP3 tensor. And here we define psi t as the expectation of x and AT follows the same kind of idea with being distributed according to pi tx. And then we have the outer product between xt transposed and AT transposed. So this is going to be a tensor now. And then our estimator is going to be theta hat. And this uses the inverse of a tensor, which is rigorously defined in the paper. You can look it up. But the idea is if the inverse of a tensor acts on the tensor itself, then we're going to obtain some identity tensor, which is not going to do anything. And then you can tell the inside here xt transposed theta t at, this is exactly the information that we're going to receive. So this is actually a valid estimator given the information we have. Right. And then you might be able to spot here that to show that this is unbiased, the first step is we're going to do after plugging in the expectation of theta hat t is we're going to use this lemma 7, and we can rewrite xt transposed theta t at transposed as the vector xt transposed combined, outer product combined with at transposed, acting on theta t. And then the vector psi to the minus 1 is acting on this entire construct. And we can plug in the definition of psi t, which we can do by putting the expectation inside, which is fine because all of these operations are linear. And then this tensor product is going to be associative, which is also something we're showing rigorously in the paper. And we have psi minus 1 acting on psi, and then the resulting tensor is acting on the matrix theta t. And because it's the inverse tensor, this is just going to reduce to calligraphic I, which is the identity tensor in the tensor space. And then we just get theta back. So our estimator is indeed unbiased, as we're expecting. And now regret in this setting is going to be with the same kind of parameters we had earlier, this term. All right. Next, we're going to come to matrix geometric sampling. You can tell that the estimators we used so far not only rely on an expectation, but on the inverse of an expectation. And computing the expectation might be infeasible. Think of continuous context spaces, for example, and inverting a matrix can be expensive. So we adapt the matrix geometric resampling process, originally due to Neu and et al., and we are able to obtain a biased inverse of the expectation by following this procedure down here. We slightly generalize this, but it's essentially the same idea as proposed in that paper. Next, we are going to need a sampling scheme to make this run. And in the first case, our sampling scheme is simply selecting, this is for CO2 FDR, is simply selecting drawing x from D and drawing A from pi t given x. And then we simply output A in the kth element of A times xt transposed. And you can tell that this is going to give a biased estimate of the expectation of this value, which is going to be a bias estimate of capital sigma tk to the minus 1. And then very similarly, the sampling scheme for expt tensor is going to be of the same nature, except we did not define the MGR for a tensor. Instead, what we're doing is we are taking xt transposed outer product at, which is going to be a tensor, and we are flattening it down to a matrix in 2 dimensions of size dk. And then we're running it through the MGR to obtain the biased estimate, and then we can unflatten this back to a tensor. We are also presenting lower bounds in the paper. We are considering lower bounds in terms of orthogonal algorithms. Colloquially speaking, if two contexts, xt and xs, are orthogonal, then we cannot use any information from round s in round t. So if you imagine basis vectors as context, then it's quite obvious that if the basis vectors are orthogonal, then you cannot use any information from that previous round in your current prediction. And the algorithms here are presented are orthogonal algorithms. And the lower bounds are then going to be given here below. And you can see that our algorithms are tight up to this m sigma squared log t divided by lambda mean of sigma factor. And if specifically, if you pick lambda mean of sigma to be 1 over d, which can be in the lower bound construction, for example, then we have a square root m gap. Thank you for your attention. This is my reference.